Welcome everyone to lecture 9. So today we're going to talk about tensor product representations. So first recall the notion of tensor product. So if V and W are vector spaces, their tensor product, V tensor W, denoted like this, is the sum of linear combinations of the vectors, which we write of the form Vi tensor Wj, where Vi is in V and Wj is in W. And this notation is linear in the first coordinate. So if we tensor CV1 plus CV2 with W, it's just so it's linear in that coordinate and also in the second coordinate. So if we have V tensor D1W1 plus D2W2, that's linear. Okay, and if V has a basis of D vectors, V1 VD, and W has a basis of D prime vectors, W1 up to WD prime, then the basis of the tensor product V tensor W is all the basis elements Vi tensor Wj. Okay, so it has that dimension D times D prime. Okay, so with that, so after recalling that, let's talk about tensor product representations. So say that we have two groups. So G and H are groups with matrix representations X and Y. Okay, then we want to define a representation of the direct product of the groups. So we want to build a representation of the direct product G times H. So these are all the pairs G comma H, where the first coordinate is in G and the second coordinate is in H. Okay, and so so the way we define it is we denote it by X tensor product Y, and it's defined in the following way. So the corresponding matrix associated to the pair G comma H is going to be the tensor product of the matrices YH. Okay, where again, if we have two matrices, then so we let A tensor B is the matrix of the form Aij B. Okay, so we scale so we scale the matrix B by the entry Aij. So this will have so if A is size if it's A is size R times S and B is size M times N, then this is going to be of size R times M times S times N. Okay, so recall the tensor product of matrices. Okay, and so we have to check that this is indeed a representation. So that's our first result. So we two things. So this map from the direct product of G cross H to matrices is let's check that it's a matrix representation. So this is a matrix representation of G cross H. And the second one is about the characters. So if X and Y, if these matrix representations have characters chi and phi, then the character of X tensor Y is, well, we're going to denote it by this. So the chi cross psi, and the value at G comma H is going to be the product of the characters. So chi times psi of H. So we just multiply these traces. Okay. So that's so let's show this. Okay, so let me just keep the definition here. And let's move this here. Okay, so why would this be true? So let's go over the proof. So I guess I'll leave it as an exercise to show that if you apply this to the identity, you get the identity. So if you apply it to E of G of H, you have to check that this is the identity matrix. So I'll leave this as an exercise. Let's check the second property, that it works well with multiplication. So if we have, so say we apply it to the product GH times G prime H prime. Well, that's this. Well, the way the multiplication works is it works coordinate-wise. So here we're applying this to G prime H prime, and this is going to be by definition the tensor product of the matrices X G prime and Y H prime. And because these are matrix representations, I can break X G prime as X, the product of the two matrices X G and X G prime, and same for Y. Okay. And then I think a lemma we saw last time says that that we can write this this tensor product of matrices. We can write it as the product of the matrices XG YG tensor times X G prime tensor Y H prime. Okay, and so this first value is the character it's the character of X tensor Y on G, and this is not the character, sorry, the matrix of X tensor Y at G, and this would be the matrix of X tensor Y at GH prime. Okay, so so just to finish. Oh. So if I do this, then I have that this is X tensor Y of GH times X tensor Y at G prime H prime. Okay, so that shows that X tensor Y is a representation. Okay, now for the second part, so about the characters. So let's see about the characters. So let's talk a little bit about the characters. That out of the way. So we need to show that the characters is a product of the characters. Okay, so we need to show this. Okay, so let's do that. So well, if we're going to compute the character, let's denote it by this form of G. So we need to take the trace of this tensor product of matrices. So this is the same as the trace of XG tensor YH. Okay, so what is this? So I guess here, so what is this trace? So if XG, if A is equal to XG, and B is equal to YG, then the trace of A tensor B would be the sum from I1, let's say that X has degree D, of AII, sorry, would be the, so we're adding over the block matrices in the diagonal, so this would be the trace of AII B, okay? And this is the same as summing over 1 and 2D AII trace of B, okay? So we can take the trace out, okay? The trace of B out, and we get the sum from I equals 1 to D of AI, and this would be the trace of A. So we get the product of the trace of B times the trace of A, and this would be the character psi of G, of H, sorry, and trace of A would be the character of G. Okay? So we showed that the trace of these tensor product of matrices is the product of the traces. Okay? So the character is just the product of the characters. Okay, so that finishes our proof. Okay? So just remember what these matrices are. You have A11B, and here you have ADDB. Okay? So for the trace, we just compute we just sum the entries here. Okay? And that's what we did here. Okay. Great. So let's continue. Okay. We always have a module counterpart. So what's the module counterpart? So if V is a G module and W is an H module, then by taking the tensor product of the vector spaces, this is going to be a module of the direct product of G and H. Okay, and the way the action would work is, if you want to know what the action of G comma H is on the vector V tensor W, okay, then it would just be the tensor product of the corresponding vectors GV and HW. Okay, and if we chose a basis for V and a basis for W, we would get corresponding matrix representations X and Y, and the corresponding matrix representation of the action of this G cross H module would be exactly the tensor products of X and Y, like we defined before. Okay, so this is exactly the counterpart, the module counterpart of this. Okay, okay. So now that we've defined this tensor product of two representations, we want to describe the irreducibles. So, what are the irreducible representations / characters of G cross H? Okay, so that's the next question we're going to answer. Okay, so let's think about it for a second. Okay, so our next result shows that they come from taking the tensor product of irreducible representations of G and H, and there's nothing else. Okay, so the first part is that if X and Y are irreducible representations of G and H, then the tensor product X tensor Y is an irreducible representation of the product of groups. Okay, And the second part of the result is that all irreducible representations of the direct product of the product G times H is exactly are exactly come from tensoring irreducibles of representations of G and H. So let's write that. So if we have a complete list are all the inequivalent irreducible representations so if this is the list of all the irreducible representations of G and H, then their tensor products are all the inequivalent irreducible representations of G times H. Okay, so we don't get more. Okay, so let's prove this result. Okay, so for the first part, well, we have a very good device for testing if a representation is irreducible or not by using the inner product. So if we get 1, when we take this inner product, then we're done. Okay, so say that x and y have characters chi and psi. Then, okay, so let's take the inner product. So let's take the inner product of the corresponding character of x tensor y. Okay, so this is the sum of the size of the group, and then we sum over all the elements of the group, and we have character value of g comma h. Oh, this is psi. So this here should be psi, and here we have the character value of the inverse. So we know that we can. Sorry, we know that we can write it like this. So we instead of using the conjugate of the same element. Okay, and now we've seen before that this character value is just the product of the characters of G and H, and this is the product of the characters. So let's use that. Okay. Okay, so let's use that. So we're here. Okay, so then this equals. So we can break this into the sum G and H, and we're gonna break each of these as a product. So we have the product of this, and I'm gonna rearrange already. So we have this big product here. Okay. Okay. Okay, so I'm going to keep rearranging this so I can split the sum. I can first sum over G. I'm going to have character of chi G and the character of G inverse, and I can have the size of H, 1 over the size of H. I sum over the elements of H, and I get psi of H inverse. Okay. And this first sum is just the inner product of the character chi with respect to itself, and this product here is the product of the character psi with itself. But these are irreducible. But x and y are irreducible representations, so chi is an irreducible character, so this is 1, and same thing for psi. So at the end, we showed that the inner product of the tensor product of characters with itself is 1. So this is an irreducible character. Okay, so we were able to show that So when we take the tensor product of irreducible representations, we get an irreducible representation. And next, we have to show that there are no other irreducible representations of G times H. Okay, so let's prove that. Okay, so, well, we know that the number of distinct and equivalent irreducible representations of G, that is the number of conjugacy classes of G, and same thing, the number of Yj's, the inequivalent irreducible representations of H, is the number of conjugacy classes of H. Okay, and now by 1, we know that each tensor product of xi yj is irreducible. Okay, and now the number of these xi yj, well, it's the number of conjugacy classes of G times the number of conjugacy classes of H. And this product is just the number of conjugacy classes of G times H. Okay? And this has to be this number of conjugacy classes is counting the number of irreducible representations of G times H. So since this tensor products xi, tensor yj are all irreducible, and I have and their number is exactly the number of irreducible representations that I should have, then I have them all. So I have them all. Okay. Okay. So there are no new irreducible representations. They all come by doing this process. Okay. Okay. Great. So in the next lecture, we're going to answer how to get a representation of G from a representation of subgroup H, and how to restrict a representation of G to a representation of a subgroup H.